Hey guys, Mr. L coming back at you with another video. And in this video, we're going to discuss calorimetry, or the idea of detecting heat through a reaction. We're going to talk about specific heat and heat capacity, Hess's law when we're starting to add up different enthalpy values, as well as what enthalpy of formation is. So let's get into this video. So the first thing we're going to talk about is calorimetry. Since we can't know the exact enthalpy values of our products and reactants, we can measure the change in enthalpy using this device called a calorimeter. And there's going to be two different kinds of calorimeters that we use. The first one is for aqueous solutions, and typically in the general chemistry lab, we use coffee cup calorimeter. So the anatomy of a coffee cup calorimeter is you're going to have two coffee cups that are seated inside of each other to form an insulative property. We're going to have some thermometer here to detect heat flow, and then we're going to have some stirring device. So we've got a little metal stirrer here. Then we're going to pour our different reactants in here, stir it up, and see the temperature change in this calorimeter, coffee cup calorimeter that we have. So the next thing we're going to talk about is the idea of specific heat or heat capacity. And heat capacity is the amount of heat that's required to increase the temperature of an object by 1 degree Celsius, which is the same as increasing by 1 Kelvin. They increase at the same rate, they're just scaled differently from each other by 273.15. So we're interested in the change in temperature. So if the temperature increases by 1 degree Celsius, it's the same as increasing by 1 Kelvin. So let's talk about an example of heat capacity. If we have something like water, water's heat capacity is 4.18 joule per gram Kelvin. So that means if we have 1 gram of water, it's going to take 4.18 joules to increase the temperature of that water by 1 degree Celsius, which is the same as 1 Kelvin. So if we have 1 gram of water at 15.5 degrees Celsius, and we put in 4.18 joules of heat, which is 1 calorie, it's going to increase to 16.5 degrees Celsius. So we can use this property of water, which is going to be important for our coffee cup calorimeter. Most of the things that we put in the coffee cup calorimeter are going to be aqueous solutions, so they're going to be dissolved in water. So if we're remembering our system and surroundings, the system's particles are going to be dissolved in the surroundings, which is the water. So our thermometer is going to be dipped in the water, and if we had an exothermic reaction, that water's temperature is going to increase. Therefore, we're detecting the surroundings, and we're going to see an increase in temperature. So we could use this equation: specific heat is equal to the heat, Q, divided by mass times change in temperature. So we could rearrange this in terms of Q, and we're just going to do some algebra, and Q is equal to mass times heat capacity times the change in temperature. So whatever the masses of the solution, say we put 2 50 ml solutions into the coffee cup, that would be a total of 100 grams. We'd multiply by the heat capacity of water, which is 4.18 joule per gram Kelvin. And then we're going to just see our delta T. Say we had a delta T of 15 Kelvin or degrees Celsius. So you just multiply those three numbers, and we could see the heat released by this reaction. So we might not always have aqueous solutions that we want to detect the heat flow of released or absorbed by that system. So if we've got solids and liquids, typically we use a different machine called a bomb calorimeter, and they're a little bit more advanced. They're going to have a chamber in which you have your system. So it could be rocket fuel or some food item, and that's a solid like crackers. And then inside that chamber, you're going to have little wires, and it's going to catch that thing on fire and let it burn and release as much heat as possible. That inner chamber is going to be surrounded by water, and then there's going to be an outer chamber around that, where you're going to have a thermometer and a stirring device so that you can detect the heat transferred to that surroundings, which is the water. So bomb calorimetry is going to have a different equation where the heat of reaction Q is going to be equal to negative heat capacity of the calorimeter. So each calorimeter is going to have its own unique heat capacity value times the delta T of that, so times the change in temperature. So Q equals negative C cal delta T. So the next thing we're going to discuss is the idea of Hess's law. And Hess's law states that whenever you have multiple steps that have different enthalpy changes that we can get from our coffee cup or bomb calorimeter, if you got multiple steps for a reaction, all you have to do is add up all the steps, and that's going to give you your overall change in enthalpy. because we can remember that enthalpy is a state function. So all that matters is where you started and where you ended, and you can take final minus initial and get your delta H value. So instead of doing this every single time for a reaction, a lot of this has been done over however long chemistry's been around, hundreds of years. So we've been compiling data into different manuals, and we can pull different values from these manuals to find our delta H of known reactions. Like we know the combustion of methane, we know the combustion of ethane and propane. So all of these are published values, and we're just gonna have to consult a manual and find out what our delta H of reaction is for that specific reaction, and then add up all the steps. So the last little piece that we're going to need to know before we can start trying to do these calculations is what enthalpy of formation is. So the enthalpy change for a reaction in which the compound is made from different constituent elements is going to be the enthalpy of formation. If you're in the elemental form, so oxygen is diatomic in nature, O2 particle, if you have something like an O2 particle, there is no enthalpy of formation value for that. It's just going to be a 0 because it's already in its elemental form. But something like carbon dioxide, that's not in its elemental form. So if we take the delta H of formation values for the allotropes that make up carbon dioxide, we can just use those manual values. So most different labs have these chemistry and physics handbooks that are going to have all those published data. So there's been hundreds of years of information that's been compiled in these different manuals. Most textbooks, though, are going to have enough information in the back of the textbook for you to just pull these different values. So you're going to look up these different values, and you're going to see that there's delta H of formation, so it's going to be sub F with the little degree symbol on the top right. What that little degree symbol means is that we've done this under standardized conditions. We standardized the temperature and pressure in the lab so that whenever we go to do this around the world, we know that it should be the same value as long as you're under those same conditions. So standard thermodynamic temperature and pressure is 25 degrees Celsius, which is 298 Kelvin, and 1 atmosphere of pressure. So these are our standard enthalpies of formation values that you would pull from these different manuals. So now let's look at an example of how we would use these enthalpy values in Hess's law. So if we were looking at something like the combustion of propane, we're going to take 1 mole of propane, combust it with 5 moles of oxygen gas, and we're going to yield 3 moles of carbon dioxide gas and 4 moles of liquid water. So it's going to be important that you have your phases on here, because when you go to consult your manual, each different phase of that substance is going to have a different enthalpy value. So we can think about this in 3 steps that's going to happen in order for us to combust our propane. Step 1 is going to be that we take propane and completely rip it apart. So we're going to isolate our hydrogen from our carbon. So we're going to take our propane gas and rip it apart, and we're going to yield 3 atoms of carbon graphite, and as well as 4 diatomic hydrogen gas particles. And that's going to have some enthalpy value. It's going to require energy. So it's going to be a positive delta H value. Step 2 is we're going to take that carbon atom, those graphite atoms, 3 of those, and react that with oxygen. And we're going to yield some carbon dioxide gas. That's going to be an overall release of energy, because it's going to be more preferential for carbon to bond with oxygen. So it's going to be a negative value, releasing energy. Oxygen is going to oxidize the carbon. And then the last step is we would have our hydrogen gas, and that's also going to be oxidized by oxygen because it loves to rip electrons. So we're going to have a release of energy here, and we're going to form 4 moles of our liquid water. So we ripped apart propane, we oxidized the carbon atoms, and then we oxidized the hydrogen atoms. So we had 3 steps. So what Hess's law states is that all we need to do is add up our delta H values of our 3 steps, and that's going to give us our overall delta H value for the reaction. So this is how we use Hess's law. So now what we're going to do is we're going to compare that to taking the published values of enthalpy formation and doing products minus reactants from our book. All right, so if we were going to compare our delta H values from the Hess's law that we just talked about to the published values, what we're going to need to do is find the delta H of reaction, and in order to do that, we're going to sum the delta H of formations for all of our products, and we're going to subtract that from the sum of all the delta H of our reactants. So if we were to look up in our manual, carbon dioxide is one of our products, and we have 3 moles of that that's going to be produced. So we're going to take 3 moles times carbon dioxide gas enthalpy of formation value from our manual or the back of the book. And that's a negative 395.5 kilojoules per mole. Then we're going to add that to the 4 moles of liquid water, and liquid water is going to be different than water vapor, so make sure you pull the right value. And we have 4 moles of that multiplied by negative 285.8 kilojoules per mole. So then we're going to close our brackets, so that's all of our products summed together, and then we're going to subtract it from our reactant values. We've got 1 mole of gaseous propane, and that's going to be negative 103.85 kilojoules per mole. And we're going to add that to our oxygen value, so 5 moles, but oxygen's already in its allotropic form, so the value is 0. It's already existing in how it exists in nature. So anytime you're talking about allotropes, the delta H of formation is always 0. So it's going to be 5 times 0. So if we take our products minus reactants, we're going to get our overall delta H of reaction, and that's going to match up to our 3 steps of Hess's law. So this is how we pull our published values from these different manuals and calculate delta H. So there it is, you guys. There's the video on calorimetry, the idea of Hess's law, and enthalpies of formation. So if you like this video, smash the like button, send it to your favorite rock, send it to your favorite lab equipment, and we'll see you in the next video.